Flexible riser wire armor integrity assessment, evaluating structural safety of subsea riser components. Introduction to assessment procedure, agenda overview. This section introduces the purpose and scope of the assessment procedure for flooded annulus and flexible riser wire armor integrity. The procedure is designed to provide a structured, standards-aligned approach for detecting, characterizing, and analyzing annulus flooding conditions and their impact on tensile armor wires. It emphasizes compliance with API Spec 17J, API RP 17B, DNV RP F201, and DNV RP F204, as well as OEM-specific guidelines. The introduction explains that annulus flooding can lead to severe corrosion, fatigue, and mechanical damage, which compromise riser integrity and operational safety. The assessment aims to ensure fitness for service, FFS, decisions are based on robust data and engineering analysis. Key objectives include identifying annulus status, dry, suspected wet, or wet, evaluating wire armor condition, quantifying remaining strength and fatigue life, and defining mitigation strategies. This section also sets the tone for the presentation by highlighting the importance of integrating inspection results, operational data, and environmental factors into a comprehensive integrity management framework. The agenda outlines the logical flow of the presentation, which includes introduction and abbreviations, references and how to use them, failure modes considered, inspection and monitoring program, engineering integrity assessment, acceptance criteria and deliverables, workflow visualization through a flowchart, and practical notes and next steps. Each section is designed to build upon the previous one, starting with foundational definitions and moving toward detailed analytical steps and decision-making processes. The agenda ensures that participants understand the comprehensive nature of the assessment and the interdependencies between inspection, analysis, and operational controls. By following this structured agenda, stakeholders can appreciate the technical rigor and governance requirements embedded in the procedure. Key definitions, objectives of the assessment, abbreviations and terminology. Flexible risers are unbonded, multi-layered pipes used to connect subsea facilities to topsides, comprising layers such as carcass, pressure sheath, tensile armor wires, tapes, and outer sheath. The annulus refers to the space between the pressure sheath and outer sheath, typically non-pressurized, housing armor wires and tapes. Annulus flooding occurs when seawater enters this space through breaches or venting defects, creating conditions for corrosion and microbiologically influenced corrosion or MIC. Wire armor integrity denotes the structural health of tensile armor wires, considering corrosion, fatigue, fretting, and mechanical damage. These definitions are critical for understanding the degradation mechanisms and their implications on riser performance and safety. The primary objectives of the assessment include detecting and confirming annulus flooding status, characterizing armor wire condition and degradation mechanisms, quantifying remaining tensile capacity and fatigue life under degraded conditions, establishing risk ranking and fitness for service decisions, and defining monitoring, inspection, mitigation, and repair strategies. Common abbreviations used in this procedure include FFS, fitness for service, MBR, minimum bend radius, MIC, microbiologically influenced corrosion, N_EFF, effective number of intact armor wires, PC, pulsed eddy current, ACFM, alternating current field measurement, VIV, vortex-induced vibration, and TDP, touchdown point. Understanding these terms is essential for interpreting technical discussions and ensuring consistency across documentation and communication. The abbreviations section serves as a quick reference for stakeholders and auditors. Applicable standards and how to use them, failure modes considered. The assessment procedure relies on key standards such as API Spec 17J for flexible pipe design, API RP 17B for operations and integrity management, DNV RP F201 for fatigue analysis, and DNV RP F204 for integrity management frameworks. OEM manuals provide specific instructions for annulus monitoring, venting, and acceptance criteria. NACE or AMPP guidelines inform corrosion and MIC management, while IMCA notes guide ROV inspections. ASTM standards govern NDT methods like PEC and ACFM. Practitioners should use the latest controlled editions and adopt the most conservative requirements when standards diverge. This approach ensures technical robustness and compliance with industry norms. The assessment considers multiple failure modes, including annulus flooding leading to armor corrosion and wire fatigue due to dynamic bending at hang-off, wave zone, and touchdown point, as well as vortex-induced vibration, fretting and wear between layers, thermal and chemical degradation affecting pressure sheath and annulus gas behavior, mechanical damage such as outer sheath cuts, end fitting issues, birdcaging, and wire breaks, and buckling or overbend risks if MBR or stiffener performance is compromised. Understanding these failure modes is essential for developing effective inspection strategies and analytical models that accurately predict remaining life and structural integrity. Detection and characterization techniques, classification and monitoring strategy. Inspection techniques for detecting annulus flooding include annulus vent monitoring for gas composition, CH4, CO2, H2S, O2, humidity, and dew point measurements, vacuum/hold tests, and pressure response analysis. ROV inspections focus on outer sheath condition, end fittings, splash and wave zones, and touchdown points, including strakes and fairings. Thermal imaging and operational data reviews help identify anomalies. Fluid sampling for chlorides, pH, sulfides, and biological activity assesses corrosion and MIC risk. Acoustic and electromagnetic methods like PEC and ACFM provide indirect evidence of wire condition. These techniques collectively enable accurate classification of annulus status and inform subsequent engineering analysis. Annulus status is classified as dry, suspected wet, or wet based on inspection data. Dry status indicates normal gas composition and successful vacuum hold, while wet status confirms water presence, H2S detection, or vacuum failure. Monitoring strategies include establishing a baseline with vent gas profiles and ROV visuals, conducting short-interval follow-ups for wet status, and implementing risk-based periodic ROV inspections. Trigger-based inspections occur after storms or abnormal operations. This structured approach ensures timely detection of changes in annulus condition and supports proactive integrity management. Analytical steps and inputs, deliverables and acceptance criteria. Engineering assessment begins with gathering inputs such as as-built data, OEM protocols, operational histories, environmental conditions, and inspection results. Analytical steps include screening and risk ranking, corrosion assessment to define rate envelopes and section loss, remaining strength checks using N_EFF and combined load cases per API 17J and 17B, and fatigue reassessment using DNV, RP, F201 methodologies. Consequence and risk evaluations inform mitigation strategies, which may involve sheath repairs, annulus drying, chemical treatments, load management, or riser replacement. Acceptance criteria are based on API and OEM standards, ensuring decisions are technically justified and auditable. Let's see this flow process diagram of analytical steps and inputs. Step 1 is to gather inputs, compile original equipment manufacturer or design data, operations history, metocean or vortex-induced vibration, and latest inspections, gas, dew point, vacuum test, remotely operated vehicle. Step 2 is to initial screening and risk ranking, prioritize based on age, dynamic severity, service criticality, and current annulus evidence. Step 3 is to annulus status decision, classify as dry or suspected wet or wet using current measurements and visuals. Step 4 is to, if dry, maintain baseline monitoring, periodic venting or gas or humidity, and perform fatigue screening. Step 5 is to, if suspected wet, execute annulus tests, gas composition, dew point, vacuum or hold, and water sampling. Step 6 is to, if wet, implement immediate controls, increased monitoring frequency and plan mitigation or repair. Step 7 is to corrosion assessment, establish corrosion rate bounds and estimate section loss, uniform or pitting. Step 8 is to fatigue reassessment, recalculate remaining life using DNV, RP, F201, updated stresses, and S-then factors. Step 9 is to remaining strength check. Compute effective number of intact armor wires and verify against API 17J and 17B or original equipment manufacturer limits for combined loads. Step 10 is to meets criteria. If yes, document FFS and set KPIs/intervals. If no, define mitigation or repair actions. Step 11 is to mitigation or repair plan. Options include sheath clamp, annulus drying or purging, microbiologically influenced corrosion control, load or vortex-induced vibration management, or replacement. Step 12 is to reassess post-mitigation, verify improvements and loop back to acceptance decision as needed. Step 13 is to update IM plan and closeout, update IM documents, inspection strategy, triggers, and issue closeout report and handover. Key deliverables include an annulus flooding status report, wire armor integrity report detailing remaining tensile capacity and fatigue life, updated risk register and FFS statement, mitigation and repair work packs with OEM approvals, revised inspection and monitoring strategies, and management of change documentation for operational envelope adjustments. Acceptance criteria require annulus dryness, stable dew point, absence of H2S, and successful vacuum hold. Structural margins must meet code requirements even with degraded sections, and fatigue life must exceed company minimum thresholds. These deliverables and criteria ensure transparency, compliance, and effective integrity management. Acceptance criteria. For annulus, no free water, stable dew point, non-detectable hydrogen sulfide or H2S, successful vacuum hold per original equipment manufacturer and API RP17B, recommended practice for unbonded flexible pipe. Strength, code-required margins met with degraded section properties or effective number of intact armor wires. Fatigue, remaining life exceeds minimum company criterion, for example next inspection interval times factor. Monitoring. KPIs within alarm thresholds, dew point, oxygen or hydrogen sulfide, remotely operated vehicle anomalies, strake loss. Flowchart of analysis procedure, practical notes and pitfalls. The flowchart provides a visual representation of the assessment workflow, starting from input collection and risk screening, through annulus status determination and testing, to corrosion and fatigue analysis, remaining strength checks, and fitness for service decisions. It highlights feedback loops for mitigation and reassessment, ensuring iterative improvement. The diagram simplifies complex processes into clear steps, aiding communication among multidisciplinary teams and supporting training initiatives. By following this structured workflow, organizations can maintain consistency, reduce errors, and enhance decision-making transparency. Practical considerations include trending dew point and gas composition rather than relying on single readings, promptly addressing MIC indicators, ensuring comprehensive ROV coverage of end fittings and critical zones, maintaining VIV suppression devices to prevent accelerated fatigue, and coordinating with OEMs before implementing annulus drying or chemical treatments. Common pitfalls involve inadequate data collection, misinterpretation of vent readings, and failure to update integrity management plans after significant findings. Adhering to these best practices minimizes risk and ensures compliance with industry standards.